This is video 4 in the AC theory unit, and in this video we're going to look at inductance. Now, an inductor is any sort of component that can store energy in a magnetic field, and it's usually a coil of wire. But as you can see in this picture, just a single wire just wound around some sort of former can be an inductor and can induce current. So inductance is the property of that conductor that will cause an electromotive force to be generated by the rate of change of current. So if we change the current in that coil or that conductor, it will generate an EMF, and that is known as inductance, that ability to do that. Its unit is the Henry. So 1 Henry is the inductance of a coil in which an EMF of 1 volt is induced when the current flowing in the circuit changes by 1 amp in 1 second. So it's the rate of change of current, how fast it changes. Now there are 2 laws of inductance that we're going to look at. The first one is Faraday's law, and he says that any change in the magnetic environment of a coil of wire will cause a voltage, EMF, to be induced in the coil. No matter how the change is produced, the voltage will be generated. So that can be written by a formula that the voltage will be equal to N, which is the number of turns, times the rate of change of magnetic field against the rate of change of time. So the faster we can change that magnetic field, the more voltage will be induced. The change can be made in a number of different ways. We can move a magnet within a coil, or we can move the coil relative to the magnet. It's all about there being a relative movement between the coil and the magnet. The second law is Lenz's law, and he says that an induced current in a closed or conducting loop will appear in such a direction that it opposes that change that produced it. So if we look at this diagram, if we move that magnet towards that ring, the magnetic field is going to induce a current in that ring, and that current is going to produce a magnetic field in that, and you can see that in the second diagram on the right. It's going to produce a magnetic field that's going to try and repel that magnet. So the thing that's produced is in opposition to the thing that's producing it. The factors affecting the inductance of a coil, so how good it is at generating an EMF with a change in current. We get this formula L, which is the inductance, is N squared times mu times the area divided by the length, where N is the number of turns, and then we got the permittivity of the core material, the area of the coil in meters squared, and the length of coil in meters. Now you see it's N squared, so the number of turns is the biggest factor in determining the inductance. The more turns we can get there, the more inductance. Changing the core material will also change the inductance. If it's a bigger area, bigger inductance. The longer the coil, so that L at the bottom of the formula, actually weakens the inductance. So we want that coil, lots of turns, and a short length. The creation and effects of back EMF of inductor in the circuit. If we apply a voltage to a coil, the EMF that's produced will be in opposition to that applied voltage. So that follows Lenz's law, that the EMF that's produced by a coil will be in direct opposition to the applied voltage. And there's some words there that says the back EMF is induced to oppose the original voltage. The inductive time constant of a coil. Now we've looked at the inductive time constant of a capacitor, and that was all about the voltage rising 63.2% and taking 5 time constants to charge. Well, it's very similar in a coil, an inductive coil, the inductive time constant is all about the current reaching its maximum value. So the inductor will try to oppose that current change. And so it's going to take time for the current to go from 0 to its maximum. And the time it takes is relative to this time constant, which is L divided by R. So the inductance divided by the resistance will give us that one time constant. The total time it takes to rise to maximum, is going to be 5 times that time constant. Similar to a capacitor that was 5 times the time constant to fully charge, this is 5 times the time constant to reach maximum current. And we can see that in the graph there. It reaches 63.2% after 1 time constant, and after 5 time constants it reaches near maximum. Inductors in series, well, they act the same as resistors in series. So we just add the values. So the total inductance is going to be L1 plus L2 plus L3, etc. In parallel, they act like resistors in parallel, and we need to do the 1 over L1 plus 1 over L2, and that will give us a value for 1 over L total. So again, like resistors, use that x to the minus 1 button on your calculator to add the inductors in parallel. Self-induction. So when a coil on its own, if we turn that coil off, turn the current off, the magnetic field collapses, and that will induce an EMF into itself, into that one coil, and we call that self-induction, where it produces the EMF in itself. Mutual induction is like a transformer, where the magnetic field of one coil is going to influence a second coil or a second conductor, and it will induce an EMF into that second one, and that's known as mutual induction. When we have an inductor in a AC circuit, what it's going to do is going to put the voltage and the current out of phase. Now, we said earlier on that time constant that it takes time for the current to reach maximum. And so if you look at the phasor diagram, we have the voltage as reference, and we have the current lagging by 90 degrees, because it's going to take that 90 degrees for the current to reach its maximum value, to catch up with the voltage. So in a purely inductive circuit, the current lags the voltage by 90 degrees. And you can see that with the sine waves. You see the blue applied voltage, and then 90 degrees later you see the grey of the current. So the peak of the current is 90 degrees behind the peak of the applied voltage. So an inductor in a circuit will actually oppose the current, and like resistance in a DC circuit opposes current, inductive reactance is a resultant of that inductance of a coil, and it's going to oppose the current. Also measured in ohms, like resistance, XL is equal to 2 pi FL. So XL is the inductive reactance, 2 times pi times the frequency of the supply times the inductance of the coil will give us the value of XL. The current is proportional to 1 over XL. So if XL increases, the current flowing in the circuit will decrease. And similarly, if XL decreases, the current in the circuit will increase. Similar to resistance and current. So the current in an AC circuit is inversely proportional to the inductive reactance caused by an inductor. There's our formula again. XL is 2 pi FL, and let's have a look at what happens with the frequency, change in frequency. So if we increase that frequency, then the reactance is going to increase. If we decrease the frequency, then we're going to decrease the reactance. So XL is proportional to frequency. increase frequency, increase XL. We can use inductors in all types of circuits. One of the most common one is in a fluorescent lamp circuit, and it's used as the ballast. You'll hear it referred to as a ballast, and it limits the current once the lamp has struck. So inside the ballast will be a coil that will have inductance and it will have resistance, and they will come together. We'll see that a little bit later, and they'll be known as impedance, and that will be the total opposition to the current. So the actual current flowing is going to be V divided by Z, voltage divided by the impedance. The choke is also used as a controlling element. It's actually used to give us the high voltage at the start to strike the lamp, and it does this by self-induction. So we have a collapsing field within that coil that induces a large voltage that is a big enough voltage to strike the lamp. We saw in the previous unit, DC power supplies, that the inductor can be used as smoothing in a rectified circuit. So in that diagram there, we've got the raw DC, and if we put an inductor in series, then that will tend to oppose that current change, and it will smooth out the voltage, and we'll get a relatively smooth line with just a single inductor. It can also be used in a solenoid, so we can energize the inductor, it becomes magnetized, and it can pull an armature towards it, and that armature can act on something that will make or break a circuit. So this kind of thing is used in relays, contactors, solenoid valve, buzzers and bells, and actuators. So we use the magnetic properties to form the circuit to make and break contacts.